All right, so last time we said for an electron that we can't know the position and its velocity, which is directly related to the energy of the electron. And so this is formalized in what's known as the Heisenberg uncertainty principle. And so what this states is that delta x times mass delta v is greater than h over 4 pi. So let's take a look at this. So this delta x is your uncertainty in position. So the more uncertainty you have, the bigger value this is. The less uncertainty you have, the smaller the value is. This right here is mass. And so when this number is big, the other two uncertainties can be very small. So we'll go over that a little bit later. And this right here is uncertainty in velocity. So uncertainty in velocity, you can think of that as uncertainty in energy or uncertainty in momentum. And what you see here, that it has to be greater than 0. So this number cannot be 0. We cannot have our uncertainty be 0. And that's a pretty nutty idea. If you think about kind of everyday things, we can know the position and the velocity of things. So that's, to say that we can't is pretty crazy. And that's only true for very small things. You see this mass component. So when this mass component is big, when you're talking about something like a baseball or a cell, these uncertainties can be very small and you'll still be greater than h over 4 pi. But when this mass is very tiny, like an electron, then these uncertainties must be pretty large in order to be greater than this h over 4 pi. And so this is kind of summarized by this Dirac guy. And I like this quote, it's pretty elegant. So he says, there is a limit to the fineness of our powers of observation and the smallness of the accompanying disturbance, a limit which is inherent in the nature of things and can never be surpassed by improved technique or increased skill on the part of the observer. So what he's saying here is that since we still live in the physical world and since electrons are so tiny, there is no way we can measure an electron without interacting it and without disturbing it. And so as soon as you disturb it, you kind of change where it was. And so there's no way to figure out what its original state is. And so again, just to restate this uncertainty principle, what we say is the more we know of where an electron is, and remember that's position, that's this orange part here, the less we know of its velocity. And velocity is directly related to energy, and vice versa. So you can know where the electron is, but then you can't know how much energy it has. Or you can know how much energy an electron has, but then you can't know where it is. And so what is said is that these two things are complementary. The wave and the particle nature are complementary. And so what that means is you can only have one or the other. So sometimes this thing's going to behave like a wave, sometimes it's going to behave like a particle, but not both at the same time. So we're sometimes a wave, sometimes a particle, depending on the experiment, but we're not both at the same time. So this is a pretty crazy idea, but it's true time and time again. And so you may have heard of another analogy of this, and that's Schrodinger's cat. And so in quantum mechanics, we say that an electron is a superposition of both a wave and a particle. And it's not until you observe the electron that it will pick whether it's going to behave like a wave or a particle. And so Schrodinger came up with this kind of thought experiment. He said, if you put a cat in a box with some poison, right, that has a 50-50 chance of going off and killing the cat, that until you open the box, the cat is both alive and dead. And so if you think about this logically, you'd say that's stupid, right? The cat is either dead or alive. It doesn't matter whether I look at it or not. The cat is either dead or alive. And there's ways we could tell if the cat is dead or alive. You know, leave it there for a while and see if the body decomposed or something like that. So this thought experiment comes off as absurd. It doesn't make any sense. And that's because we're thinking about it in terms of kind of logic and our interpretation of the physical world, but our interpretation of the physical world is that of a big one, right? So this is big things. And so this falls under classical mechanics, right? So under classical mechanics, right, we say the cat can't both be alive and dead at the same time. That doesn't make any sense. It's either alive or dead. You watching it has no effect. But that's not true in the quantum world. That's not true in the quantum world. The electron is both a wave or a superposition of a wave and a particle until we interact with it. And the only way we can see it is through interaction with it. So this describes little things. And so this is quantum mechanics. And so what Schrodinger was trying to point out is that trying to do this kind of thought analogy, it won't make sense, right? It doesn't make sense. It's illogical. But when we do these experiments, we see it's true time and time again, and that these experiments give us great predictive power. And so when we're thinking about little things, when we're thinking about quantum mechanics, the thing we have to realize is that we have to think differently. Things behave differently. So you can't use your logic and reasoning and apply it. Big things behave different than little things. So the whole overall point of this thought experiment is for it to be absurd. And it's to point out that when you're talking about quantum mechanics, you have to think differently. So must think differently when we want to know how small things work. And again, we have the uncertainty principle, the uncertainty in position times the mass times the uncertainty in the velocity has to be greater than h over 4 pi. And so this mass is where it kind of comes in, right? When we have a small mass, then the uncertainty, the delta x and the delta v must be significantly large for this to be greater than h over 4 pi. So the uncertainty is significant, right? When the mass is large, the uncertainty is tiny, and so there's essentially no uncertainty. Right, and so again, that's just highlighting that we have to think differently when we're thinking about quantum mechanics. You can't just say that doesn't make sense because experiments time and time show that this is true. And just one thing, right? Velocity is directly proportional to kinetic energy. So position and energy are complementary for an electron. Right, so we can't be certain about both. And so if this stuff, again, is confusing, kind of mind-blowing, that's fine. It is pretty crazy stuff. Pay attention to the homework in terms of what do I actually have to know. But if you find this stuff interesting, you know, try going down the rabbit hole of Wikipedia and YouTube videos. It's pretty crazy stuff.